You are watching a basketball play broken down by AI frame by frame. Every player tracked, every jersey number read, every shot classified as made or missed. In this video, I'll show you how to build this system step by step using RF-DETR, SAM2, and small VLM. Basketball is tough for vision. Players move fast, overlap often, and jersey numbers are small, blurred, and frequently occluded. To handle this, we combine several state-of-the-art open-source models into a single pipeline. Our goal is to build a complete system that identifies every player, knows their team, tracks their movements, and automatically classifies the result of every shot. We'll start with RF-DETR for robust object detection. Since traditional tracking is unreliable in this high-speed, high-occlusion environment, we'll leverage SAM2 for stable, pixel-level player tracking. And to identify teams, we'll deploy an unsupervised clustering pipeline built around SigLIP, UMAP, and k-means. Once players are tracked, we move on to jersey number recognition. We'll fine-tune the compact vision language model, small VLM2 for OCR, and learn how to pair those detected numbers with the correct tracked player. Finally, we map players onto the court. We train a custom model to detect 33 characteristic points on the court. We use these points to calculate the homography matrix and perform the homography transformation that projects player positions from the 2D video frame to an accurate, standardized 2D court layout. This delivers a full top-down tactical visualization, so we know precisely who is doing what and where on the court. This build took months, roughly 1,000 hours of collective work. You will see the full process from data preparation and model fine-tuning to model deployment. Let's start with object detection. For object detection, we use RF-DETR-S. It offers a strong balance between speed and accuracy. On Coco benchmark, RF-DETR-S reaches higher accuracy than YOLO 11L, while running almost twice as fast. Since RF-DETR uses DynoV2 as its backbone, the model converges faster and generalizes better to new domains like basketball. Our dataset includes 10 classes. Two main ones are player and jersey number. We use the player class to detect athletes on the court, and we use the jersey number class to locate digits that we will later read and assign to players. The player class is divided into several subclasses such as player, player in possession, player jump shot, player layup dunk, and player shot block. These subclasses will let us determine who is dribbling the ball or who is taking the shot. We also include ball, rim, and ball in basket. These classes will let us determine the result of each play later in the pipeline. All images come from 1080p video clips. Each clip contains a single live ball play. Each frame got resized to 640 by 640 resolution, and we used resize with fill to match the square input expected by the model. We don't apply extra augmentations. RF-DETR uses DynoV2 as its backbone, which gives strong performance without heavy data transforms. This is different from typical YOLO-style training, where aggressive augmentation is common. Once the dataset was ready, we moved to fine-tuning. I trained my RF-DETR directly on the RoboFlow platform. By the way, all models in this tutorial are already trained and free to use. You will find links to each of them in the description. And if you want to learn how to fine-tune RF-DETR in Colab, there's a dedicated tutorial as well. To start, we click Custom Train, select RF-DETR, and click Continue. Next, we choose the model size. I pick RF-DETR-S and click Continue again. We then initialize the run from a public checkpoint and launch training. Depending on dataset size and image resolution, the process takes a few hours. When training finishes, the model appears in our RoboFlow workspace, ready for deployment. Next, we load the model for inference. I'll be using Google Colab, where the inference Python package is already installed. It loads models from RoboFlow Universe and saves you a lot of headache by handling hardware optimization for you. To load the model, we import getModel and pass our model ID and API key. The model ID can be copied directly from the project URL. It includes the project name and model version. To get your API key, open your account settings, select the correct workspace and copy one of the existing keys or generate a new one. Then, in Colab, open the Secrets tab and paste your key under the variable name RoboFlow API key. Now the model is loaded and ready. Let's run inference on the first frame of our video. We already downloaded a small sample of 10 video clips from our dataset into the Colab environment. We'll use Supervision's frame generator for convenient frame access. All we need to do is pass the source video path and call next to extract the first frame of the video. We call the infer method of the model and pass the frame as an argument. We can also set confidence and IO thresholds to control prediction precision. The output is assigned to a variable, then converted to a supervision detections object using the from inference method. To visualize the results, we use supervision annotators. We create a box annotator and a label annotator, configure colors, line thickness, and text color, and apply them to a copy of the input frame. You can adjust these settings to improve contrast or text readability depending on your footage. If we don't specify custom labels, the annotator uses the class names by default. Supervision also allows easy filtering of detections based on conditions like class. For example, the class number corresponds to class ID 2. If we want to display only jersey numbers on the frame, we set our filtering condition to detections class ID equals 2. Filtering players is a bit more complex because, as mentioned earlier, they are split into several subclasses which map to class IDs 3, 4, 5, 6, and 7. In this case, we use numpy's isn function, passing detections class ID and a list of the IDs we want to keep. This output will serve as the input for the tracking step with segment anything tool. Traditional trackers like sort use bounding boxes detected across consecutive frames to estimate object motion using Kalman filter. Filter predicts where each object should appear in the next frame, and then new detections are matched to those predictions using IOU overlap. More advanced trackers like deep sort or ByTrack add embeddings calculated using object crops to add visual similarity, which should help when motion cues alone are unreliable, such as during occlusion or rapid movement. Sports scenes are among the hardest settings for tracking because players move fast, frequently overlap, wear similar uniforms, and often leave or re-enter the camera's view. SAM2 performs much better than regular trackers because it doesn't rely on predicted motion or detection matching. Instead, it remembers how each object looks across frames at the pixel level, capturing details like shape, color, and texture, which are stored as high-dimensional visual embeddings. This allows it to follow the same player even after fast movement, overlap, or temporary disappearance. This makes it resistant to occlusion, deformation, and re-entry challenges common in sports. SAM2 needs an initial prompt, such as a point or bounding box on a single frame, to start tracking an object through the video. To automate this process, we'll use detections from our RF-DETR model. Each detected bounding box becomes a prompt for SAM2, allowing us to start tracking every player visible on the court without any manual clicks. Back in Google Colab, we already have SAM2 installed. If you'd like to see a detailed setup, refer to the Colab linked in the description. SAM2 comes in 4 sizes, from the lightweight Tiny with around 39 million parameters to the large version with over 220 million parameters. For this demo, we'll use the large version to maximize tracking quality, even though it runs slower. SAM2 is by far the slowest part of the entire pipeline, and using a smaller checkpoint is one of the easiest ways to speed it up, something we'll discuss later in the video. To load the model, we import the build SAM2 camera predictor function from the SAM2 package. We then pass the paths to the SAM2 checkpoint and its associated configuration file. The inference code may look complex at first, but it follows a simple 3-step structure. First, we take the initial video frame and run inference with RF-DETR to detect all players. Each detection receives a tracker ID, which we'll use to link it with SAM2. Next, we loop over the detections and use the predictor add new prompt method from the SAM2 API. For each detection, we pass the frame index, the tracker ID, and the bounding box coordinates. This step initializes the prompts for every player we want to track. Finally, we iterate through the following frames and call predictor track, passing the new frame as input. The model returns mask logits, which represent raw segmentation scores before thresholding. We convert these logits into binary segmentation masks, wrap them into supervision detections, and visualize them using the same annotators we used earlier. This entire third step is wrapped inside a callback function that runs automatically for each video frame and saves the output as a new video file. Processing high-action basketball videos sometimes leads SAM2 to make segmentation errors. These errors often appear as masks consisting of multiple disconnected regions that are far apart from each other. For example, right after a shot or a pass, SAM2 may mistakenly include the ball or a background element as part of the player's mask. These artifacts may look harmless, but they can hurt later stages of the pipeline, such as team clustering or court mapping. To fix this, we apply a cleanup function that keeps only the main segment of the mask and remove the smaller ones whose centroids are too far away. After applying the cleanup function, the resulting masks are much more stable and reliable. They no longer contain large false segments, which makes them suitable for downstream tasks like team clustering. If you'd like to learn more about how to use SAM2 for both image and video segmentation, check out the dedicated tutorial linked below. Every basketball game is different. Different teams, different players, different uniforms, and even a different court. Training a supervised model to tell teams apart means labeling a huge amount of player data from different games, and I'm way too lazy for that. Plus, it probably still wouldn't generalize. If the team showed up in the new pink jerseys for the first time, our model wouldn't know how to handle this. We would need to extend the dataset with new data examples and retrain the model. To build a more flexible solution that works across games without any manual data annotation, we use an unsupervised learning approach to separate players into their respective teams. The first step is to prepare the data. We start by going through all the sample videos from the selected game. From each video, we extract one frame per second and run player detection using our fine-tuned RF-DETR model. For every detection, we crop the region containing the player. After extracting all the crops, we pass them through SigLIP and obtain high-dimensional embeddings. These embeddings are powerful, but too large for direct visualization or clustering. To make them easier to work with, we reduce their dimensionality using UMAP. UMAP projects high-dimensional data into a lower dimensional space, in our case, 3 dimensions, while preserving both the local and global relationships between points. That's crucial for producing consistent clusters downstream. Once we have 3-dimensional embeddings, we apply k-means clustering. K-means is a simple but effective algorithm that partitions data into a specified number of groups. Here, we set the number of clusters to 2, because we expect 2 teams in each game. If the process works as expected, the cropped player images naturally separate into 2 distinct groups. Each cluster corresponds to 1 team, purely based on uniform color and visual features. Just like in our football AI tutorial, we wrap this entire SigLIP, UMAP, and k-means pipeline into a single class called Team Classifier, which is part of our open source sports repository. This makes it easy to reuse. To run the pipeline, all we need to do is instantiate the team classifier object and call its fit method, passing in a list of player crops. Training takes only a few seconds. When it's done, we call predict to assign each crop to one of the 2 clusters. Now, let's test our team classifier. We take the first frame from our video, detect all players using RF-DETR, crop each of them, and pass these crops to the team classifier to divide players into teams. At this stage, we don't know the actual team names, but we know which players belong to the same team. Each crop is labeled with either 0 or 1, representing the 2 clusters. To map these clusters to real team names, we provide a simple external input, for example, mapping 0 to Boston Celtics and 1 to New York Knicks. This mapping allows us to visualize players from each team in distinct colors corresponding to their uniforms. By the way, a model like Qwen3VL can look at a group of players and name the NBA team they play for. I left it out to avoid extra complexity, but the problem is fully solvable with open source models. If you want to learn more, check our Open Vocabulary Object Detection with Qwen3VL notebook. The link is in the description. The code you see on screen is very similar to the one we used for tracking with SAM2, but this time, in addition to assigning tracker IDs to detections, we also assign team IDs. Since the tracks produced by SAM2 are stable over time, we only need to perform team clustering once. After that, we simply reference the stored team assignments for each video frame. To visualize the results, we rely on box annotator and mask annotator configured to color each player according to their team assignment. Inside our callback function, we split the masks by team ID and pass them to the annotators, which apply the correct colors across all frames. This step gives us a clean, color-coded visualization showing which players belong to which team. It's a key step that sets up everything that follows, mapping jersey numbers to names, detecting player actions, and building our final analytics visualizations. With players tracked and teams identified, the next step is to read the jersey numbers and pair them with correct players. Reading jersey numbers might sound simple, but in practice it's a tough task. Numbers are often small, sometimes partially occluded, and appear under varying lighting and motion blur. They can also deform with player movement or fold along the jersey's fabric. A model trained for document OCR doesn't usually expect that. We started by experimenting with Small VLM2, a compact vision language model designed for OCR and visual reasoning tasks. Because of its small size, Small VLM2 is both powerful and fast, making it an attractive candidate for our pipeline. Even though it was pre-trained mainly on document-style text, it transferred surprisingly well to basketball jersey numbers. Right out of the box, it reached 56% accuracy on our test set. That wasn't enough for reliable player recognition, and it sometimes produced impossible results like 011 or 3000 dot that do not appear on real jerseys. To improve performance, we fine-tuned Small VLM2 on a custom dataset of jersey number crops. We took frames from our object detection dataset, filtered out only the number class, and cropped the detected numbers. We then used the pre-trained Small VLM2 itself to auto-annotate those crops, creating labeled examples automatically. This gave us a multimodal OCR dataset containing 3,600 images. Each image was resized to 224 by 224 pixels, stretched to fill the square format just like we did for object detection. We uploaded this dataset to RoboFlow to prepare it for fine-tuning. Before starting training, we manually reviewed all labels and fixed mistakes. After verifying the dataset, we moved on to training. We start from the model version page. Here we click Custom Train to open the training setup. From the list of available models, we select Small VLM, then Continue. Next, we pick Small VLM 2 LoRa from the version list, confirm the choice, and proceed. Finally, we choose Train from Public Checkpoint and click Start Training to launch the run. As the model trains, we monitor progress directly in the browser with live accuracy and loss charts. Once fine-tuning finishes, the test accuracy reaches 86%, showing clear progress compared to the base model. Back in Google Colab, we deploy our fine-tuned model. Just like before, we use the getModel method from the inference package, this time passing the model ID of our fine-tuned Small VLM2, which you can copy from the project URL alongside the model. We define the prompt we'll use for OCR inference. To test it, we once again load the first frame of our source video. We use RF-DETR to detect all bounding boxes of the number class. Then we loop over these boxes, add a small padding for extra context, and crop them out. Finally, we loop over all crops and call the predict method of our fine-tuned Small VLM2, passing both the crop and the prompt as inputs. Each prediction returns a recognized number, which we can display next to the corresponding crop for visual confirmation. Once jersey numbers are detected, we need to assign them to the correct players. Player masks from SAM2 and number detections from RF-DETR are separate outputs, so we need a reliable way to match them. We'll use intersection over smaller area. IOS is similar to IOU, but normalizes over smaller region. An IOS of 1 means a number mask lies completely within the player mask, therefore we infer that number belongs to that player. We run RF-DETR for numbers and SAM2 for player masks on the same frame. We convert number boxes to masks with XYXY to mask. Then we call mask IOU batch, passing player masks, number masks, and setting the metric to IOS. The result is a matrix of players by numbers with the overlap scores. We look for pairs where IOS equals 1.0. Once we find these pairs, we plot their bounding boxes and mark each pair with a different color. The problem is that a single frame rarely gives matches for all players at once. For example, 5 out of 10 players might be matched, while the rest are turned away and their numbers are not visible. Even when the crop looks good, small VLM2 can return the wrong value on a single frame. Because of these two factors, we base number association on more than one frame. Now the final step is to match each confirmed number and team to a player from the roster. I prepared a Python dictionary listing all player names and numbers for both teams in this game. Pulling this data from the web is quick, and there are APIs you can use as well. Once we have it, we take the team ID and the logged jersey number for each tracked player, look them up in the dictionary, and retrieve the player's name. The rest is visualization using supervision to overlay names, numbers, and team colors on the video. Now that we know who is on the court, we need to know where they are on the court. And for that, we'll use homography. Homography allows you to map points from one flat surface to another. You know this idea from document scanning apps. You take a photo at an angle, the perspective distorts the page, but the app turns it into clean top-down view. We'll use the same idea here, but instead of working with documents, we'll work with basketball court. A homography defines a mathematical relationship between two planes. One of these planes can be the camera view of the court, and the other can be the top-down layout of the basketball floor. Using this relationship, we can transform any point from one plane to its corresponding location on the other. This transformation is represented by a 3x3 matrix, often called the homography matrix. To calculate it, we need at least 4 pairs of corresponding points between the two planes. Once computed, the matrix allows us to project any pixel from the camera perspective onto the flat top-down map of the court. But there's a catch. Basketball cameras constantly pan, tilt, and move to follow the play, and as the camera moves, the visible part of the court and reference point change. Marking them manually makes no sense, so we need a way to automatically detect them on every frame. That's where keypoint detection model comes in. Keypoint detection predicts a fixed set of landmarks, each defined by an ID and its XY coordinates. Think pose estimation, but the skeleton is the court layout. Since the camera rarely shows the full court, we need enough landmarks to keep at least 4 visible at all times. At the same time, the points must be easy to recognize and annotate. I defined 33 key points covering the main court features, including corners, baselines, the center, the paint, the arcs, and 1 point directly under each basket. Each point has its own index and serves as a homography reference. Labeling them was by far the most time-consuming part of this project. Ultimately, we managed to collect and annotate 850 images. In RoboFlow, we also define flip indexes to describe symmetry for horizontal flip augmentation. For example, the top left corner with index 01 corresponds to the top right corner with index 34. This ensures that when the image is flipped during training, the left and right sides of the court remain correctly mapped. Once the dataset was ready, we moved to fine-tuning. Just like with other models, we start on the dataset version page where we click Custom Train. From the list of available architectures, we select YOLO 11 and click Continue. Next, we choose the model size. I recommend medium or large. Going for extra large is overkill, and anything below medium is too low quality to use reliably for perspective conversion. Click Continue again, select Train from Public Checkpoint, and finally click Start Training. The training runs in the cloud, and you can monitor progress directly in your browser. Once it completes, your fine-tuned court keypoint model will appear in your RoboFlow workspace, ready for deployment. Let's load the model and see how it performs. We'll again use the inference package. We already imported the getModel function earlier, so we just call it and pass the model ID that matches your trained version. Next, we grab one frame from our video sample, we call modelInfer, passing the frame as input. The output is stored in a variable, then converted into a supervision keypoints object using the fromInference method. Finally, we visualize them using the vertex annotator, which overlays each predicted point as a small dot in its corresponding position on the frame. At first glance, the keypoints look scattered. Some land on real court features, others show up in random spots. This happens because the model predicts every keypoint, even when parts of the court are not visible. Occluded or off-screen points lead to noisy guesses. Each point has a confidence score that reflects how sure the model is. Visible features, like the paint or center circle, score high, while off-screen points or points occluded by the players score low. This scores allows us to filter out reliable landmarks from uncertain ones. Let's filter them out. We set the anchor confidence threshold to 0.5, which keeps only the points the model is confident about. Points we use for homography need to be extremely precise, because any error directly affects the computed homography matrix and makes the perspective conversion inaccurate. After filtering, the remaining points align neatly with visible court features and can be safely used for mapping. Now that we have both player detections and court keypoints, we can finally bring them together and map each player's position from the video frame to real-world coordinates on the basketball court. To map player position from camera view onto the court, we first need to calculate homography metrics. This matrix mathematically defines how points on video frame relate to points on actual basketball court, and to calculate it, we need 4 pairs of such reference points. The reference points in the camera view come from our keypoint detection model. Their real-world equivalents are defined manually based on the geometry and dimensions of the court. All these coordinates are stored in the court configuration class. Importantly, the order of points in the keypoint detection model result and in court configuration is the same. For example, the top left corner of the court is described by the anchor with the same index in both the keypoint model output and in court configuration. After running inference with the keypoint model, we create a mask describing which anchors have confidence above the threshold. Using this mask, we extract 2 aligned arrays, frame landmarks from the keypoint predictions and court landmarks from court configuration vertices. If at least 4 such pairs exist, we initialize the view transformer, passing both arrays as input. Inside, it computes and stores the 3x3 homography matrix that defines the mapping from the video frame to the court. Now we're ready to project player positions. We take the detections object, produced by either RF-DETR or SAM2 tracking, and call getAnchors coordinates on it to get the bottom center coordinates for each player. Then we call the transformPoints method of the viewTransformer class, passing the player coordinates. This converts their positions from image space to court space. To visualize the result, we draw the court and plot the transformed player positions using draw points on court, coloring players from each team differently. However, when we repeat this transformation frame by frame across the video, the results aren't stable. You'll notice that player positions sometimes jitter or jump between frames. Homography assumes that all mapped points lie on a flat surface, in our case, the basketball court. To locate a player on that surface, we assume the bottom center of their detection bounding box corresponds to where they touch the ground. But when the player jumps, or when 2 players overlap, the bounding box shifts upward and its bottom center no longer represents the true ground position. Even small vertical change can project to large displacements when mapped onto the court plane. To make these trajectories usable, we need to clean them. We start with two D-player coordinates across consecutive frames. When we connect these points, we get the player's trajectory, and you can immediately see how it jumps unnaturally at times. To detect those teleport-like jumps, we measure the player's movement between frames as frame-to-frame speed. We then calculate the median of all speeds to understand what typical motion looks like and compute the median absolute deviation, which measures how much those speeds usually vary from that median. If a player's movement in a single frame is greater than the median by several times MAD and also exceeds a minimum absolute distance, we flag it as unrealistic. Once we identify these outliers, we group them into short runs and pad a few frames around each to make sure we remove all noisy edges. We then rebuild those missing sections through linear interpolation, connecting valid points before and after the corrupted segment with straight lines. After restoring the basic trajectory, we smooth it using a small sliding window that fits gentle curves along the path. When applied across an entire game, this cleanup process produces smooth and reliable movement data that can be used for automatic tactical analysis. It helps reveal patterns like frequently played actions, hotspots where players appear most often, and even the total distance each athlete covers during the match. The obvious downside of this solution is that it can't run in real time. The cleanup function needs access to full player trajectory before it can decide which points to remove, interpolate, and smooth. This makes it ideal for post-game analysis, but not for real-time tracking or instant replays. The last thing I want to show you today is shot detection and result classification. We'll start with the same object detection model we trained earlier. As I mentioned at the beginning of the video, while building the dataset, we made sure to include all classes related to shooting action: player jump shot, player layup dunk, and ball in basket. These classes let us detect both the shooting motion and the shot outcome. Let's load a video frame where a player takes a jump shot and run object detection just like before. The model correctly highlights the player as player jump shot using supervision. We can easily filter detections and keep only those corresponding to that class. The jump shot label has a class ID of 5, so we pass that condition in square brackets to isolate it. Mapping this detected shot position onto the court works the same way as mapping any player position. We run the key point detection model on the same frame, keep only high confidence court landmarks, build the homography matrix, and project the detected player onto the court plane. We can then mark the shot position with the draw made and miss on court annotator. The problem is, as I mentioned before, the homography projection only works when the player is on the ground and his feet are visible. When player is mid-air or partially occluded, the bottom center of his bounding box no longer represents his true position on the court. In other words, if we detect the jump shot when the player is in the air, it's already too late. The projection will land in the wrong place and we will mark the wrong spot for the jump shot. That's where the shot event tracker from the sports repository comes in. The tracker looks at a sequence of frames and watches for consistent visual patterns. When it sees several consecutive detections of player jump shot or player layup dunk, it treats that as the start of a shot attempt. It then waits for a short window of time to see if the ball and basket class appears soon after. If it does, the shot is marked as made. If the window expires without seeing the ball in the basket, the shot is marked as missed. As a result, Shot Event Tracker gives us a reliable stream of events, start, made, or missed, each with corresponding frame ID and shot type, whether jump shot, dunk, or layup. Let's switch back to Google Colab and see how it works in practice. We load our sample video and initialize the tracker with 3 simple timing parameters that define shot duration, cooldown, and spacing between attempts. Then, as we loop through the frames, we run object detection and check for 3 key classes: jump shot, layup, and ball in basket. For each frame, we call the tracker's update method with these detections. And whenever it detects a new event, we print it and visualize the frame with bounding boxes and labels. Here's what happened in our example clip. At frame 64, the tracker logs a start event for a jump shot. At frame 115, it marks that attempt as missed. Then at frame 120, it detects a start event for a layup. And by frame 135, it records a made event. On the screen, you can see the sequence unfold. The player takes the jump shot, misses, grabs the rebound, and scores with the putback layup. We can now process longer sequences of plays to collect structured shot events, including both the type and outcome of each attempt. When combined with the homography mapping we built earlier, these events can be projected onto the court to form a complete shot chart, showing where each attempt happened, who took it, and whether it was made or missed. This creates a clear visual foundation for analyzing shot tendencies and scoring patterns. And that's all the code I wanted to show you today. This was by far the most ambitious project we ever showcased on this channel. You saw how RF-DETR, SAM tools, small VLM and SigLIP can be used together to detect players, track their movements, cluster them into teams, map their positions on the floor, and classify shots into makes or misses. All the code, models, notebooks I used in this tutorial sit in the description below, so feel free to explore them, run them with your own footage, and tweak the ideas to build even cooler stuff. If you have any questions or suggestions, leave them in the comments below. And if you enjoyed the video, make sure to like and subscribe, and stay tuned for more computer vision content coming to this channel soon. My name is Peter, and I'll see you next time. Bye.